Okay, let's have a look at Dalton's law of partial pressures. In order for us to build up this law, we need to go through a few thought experiments. In the first set of diagrams that I've got here, I have a closed system and I increase the number of particles or number of moles of our gas, and we know that by doing this we increase the collisions on the vessel, which increases the force, which increases the pressure inside that vessel. So increasing the number of moles or particles increases the pressure. Let's have a look at the second situation. We've got gas A separate from gas B. So in this particular example first, we had the same gas. But in the second example, we're going to put two gases and mix them together. Now, if we poured all of this particular gas from B into A, we've actually got the same situation as we had in the first example. So we've kept the same volume, we've used this volume, we've increased the number of particles in that volume, and it means that we've increased that pressure. So we get something like this. We've got a single vessel, we've got particles from A, particles from B, which will now give us a total pressure. It turns out that that total pressure will be equal to the pressure from here and the pressure from here to give us that total pressure. So if we represent this in an equation, we can say the total pressure of any system is equal to the partial pressure of the first system plus the partial pressure of the second system, in this case A and B. We add those together to give us the total pressure if the volume is kept constant. And this law is known as Dalton's law of partial pressures. Let's see how we apply it. So we're told that we have a mixture of gases. The partial pressure of our hydrogen is 100 kilopascals. The partial pressure of our carbon dioxide is 75 kilopascals. Our methane is 200 kilopascals. And our ethene is 65 kilopascals. We want to know what the total pressure is. So from Dalton's law, we get the formula total pressure is equal to the partial pressure of system A plus the partial pressure of B plus partial pressure of C and partial pressure of D. So we can put in our numbers and get our total pressure. Now what this is assuming is that we don't change the volume. If we change the volume, we obviously change the pressure. We know that from Boyle's law. But we're making the assumption that our volume doesn't change. So we've got 100, 75, 265, which gives us a total pressure of 440 kilopascals overall. Now we can also use this we can use this quite practically to work out what the vapour pressure is in our system as well. So vapour pressure is a measure of the pressure that relates to a liquid becoming a gas and a gas becoming a liquid. So my first diagram here, I've got a system that's in equilibrium. It's at a given temperature. It's a closed system, so the pressure generated inside is separate from the pressure outside. It's also a given volume, and we have a finite amount of particles in there. Now those particles can either be in a gaseous form or a liquid form. What we find when we're in equilibrium, some of the gaseous particles will become liquid, so they will cool down, and some of the liquid particles will become a gas. So they absorb energy and become a gas. So we get this continual flow from liquid to gas, gas to liquid. Now if we increase the temperature, we're going to increase the number of particles in the gaseous form and obviously reduce the number of particles in the liquid form. So we set up an equilibrium like this one. We actually have more particles in the gaseous form, and as we said before, if you increase the number of particles, you increase the force per unit area, which increases the pressure. So if we increase temperature, we increase the pressure, or the vapour pressure of that liquid in that container. And by contrast, if we reduce the temperature, more particles will go into the liquid form because they don't have as much energy. So we actually have less particles in the vapour form, which will lead to a lowering in pressure. Less particles, less force, less pressure. So how does this work for us practically? Because we quite often have gases, we have water in the air when we're measuring the pressure of gas as well, well, it turns out that it has quite a significant effect. If we take the vapour pressure of water at 0 degrees C, it exerts a pressure, a partial pressure in any system of 0.6 kilopascals. As we go up to 20 degrees, it's 2.3 kilopascals. 40 degrees, 4.2, and we really make a jump as we get to 60 degrees. We've got just under 20 kilopascals. At 80 degrees, we've got 47.3 kilopascals. So there's quite a rise through there. Our final value here of 100 degrees is the boiling point of water, which is 1 atmosphere of pressure. So we've got to take this knowledge if we're doing any experiment with the pressure of gases, and we actually have to work out what the temperature that we're conducting our experiment is and subtract the vapour pressure of water if we're conducting an experiment to do with gases. We have to subtract that partial pressure from any total pressure that we get to get the pressure of the gas that we're looking for. So if we rearrange that equation, Pt equals P1 plus P2, where P1 is actually the vapour pressure, we find that P2, the pressure of any gas that we're looking for, is going to be the total pressure that we calculate or measure minus that vapour pressure. So that final figure there is the pressure of the gas that we're looking for. This pressure here includes the vapour pressure of the water. That's it.